All right, now, everybody in this room has had a lizard at one time in their life run into their house. And you might try to chase it down, you might run underneath the cabinet, you try to throw your arm underneath there and grab it, you feel it wiggling around, you pull your arm out, and all you have is the tail. And the lizard gets away scot-free, and the joke's on you because they get away and they get to grow a new tail, right? And so here's a little bit about how that process works, right? And so basically all you see is that there's a scarring on the tail, and then basically over about, it says less than a year, it's actually only about in a few months, that they'll actually regrow a new tail. And that's completely 100% theirs. I have a visual real fast for you of a lizard regrowing an arm. And what's so interesting about this is it all starts with stem cells. And science has been asking for so long, why are lizards able to do this when they're such simple creatures, but humans are such complicated creatures and we don't have the ability to regrow limbs? Now, regenerative medicine is really approaching this question. But this isn't really a new field of medicine, so I'm going to kind of give you a backtrack of the history. They actually began about in the 1930s by a man named Alexis Carrel writing a book called The Culture of Organs, where he basically was able to keep embryonic chicken heart stem cells alive outside of the chicken, and that was the first time we were able to keep cells alive outside of the living organism. And this was amazing, groundbreaking stuff. You can actually see that he co-wrote this as well with Charles Lindbergh. And Charles Lindbergh just kind of worked on mechanical stuff. Here's a picture of Lindbergh and Alexis Carrel on the cover of Time magazine in the 1930s. Okay, so now what is regenerative medicine? What are they trying to solve? What's the problem that they're trying to solve? Well, what I'm focusing on is the growing of new organs. And here's the first organ transplant being done at Harvard Medical School about 55 years ago. And really, what's so amazing is that since that first transplant was done, the methods haven't changed really. We still need a donor, either alive or dead. We use the same methods, and really it might have gotten more sterile or cleaner, but it hasn't gotten more efficient. Okay, and so, and the organ transplant problem, it's not a problem just here in America. It's actually an international problem. An interesting factoid is that China actually right now, they get 2/3 of their organs from executed prisoners, and this is a highly debated topic. And so they're trying to figure out how can they get organs and be able to save their sick citizens without having to kill these prisoners. And we have the same problem here in America. This is actually a table from in Texas over the past 15 years. You can see that that this is the waitlist edition, this blue line, right? And then this bottom line, this is the donors, this green line. You can actually see there's several hundred variants of the amount of organs that we have donated and the amount of organs that we need to be donated. And at the same time, we have more additions with the increase in research in medicine to find diseases. We're seeing more and more people diagnosed with problems and no more donors. So now the next question is to ask, what are we doing to fix the problem? And well, the first step that we took to fixing the problem is something called biomaterials. And these are very, very fascinating because it's something that it looks so simple. It looks like just a piece of gauze if you were in a hospital, or a piece of cloth that would make up a T-shirt. But it does so much more than that. And this is an example of the power that's been harnessed for biomaterials. And basically, what you're able to see is that this is actually a urethra from an individual. And you can see that it's damaged. So what scientists were able to do is they were able to cut away this damaged part of the urethra, take it out, and replace it with a biomaterial, wrap a biomaterial around it. And so then what happened though is that the cells from that own person, is they use that biomaterial as a bridge to cross across, and so the biomaterial then dissolves away, and you're left with just a urethra that's 100% your own and from your own cells, and fully functional. And you have it for life. That's amazing. Another big question that was answered with that was that we're able to see that just like the lizard, humans are able to regenerate, but it's only for small distances. So we're only able to regenerate about 1 to 3 centimeters. Okay, so then what else can we do to fix the other larger problems, like kidney disease, like kidney failure, because that's the largest, that's the organ that takes up the most on the donor wait list as kidney transplants. Well, the next thing that's been done is they've actually used a mold they basically do a CAT scan to figure out what does your organ look like vaguely, and then they basically make a mold of what it should be like. And this is a mold from the first artificial trachea that was transplanted last year in Stockholm, I think about in July. And basically, after they have the mold, they'll go into your body. They'll take out some of your blood, take out some of your stem cells, adult stem cells from various methods. I guess there's adipose fat stem cells, and various methods. And then they basically, if they take your blood, they'll seed apart the cells, they'll take out the stem cells, and then they'll basically grow them exponentially in petri dishes. And then they'll take those stem cells, they'll put it on this pre-made mold that they have, which on the right, that's actually the trachea with the stem cells on it that was later implanted. And then they just put it in your body, and there's no chance of rejection because it's your body's cells. So then there's no tissue typing that goes on with organ donation. There's no blood typing that has to go on with organ donation. And so this process doesn't take very long. This process only takes about a few weeks. Okay. And the last step with this mold process is they actually have to train just kind of educated on what it's going to do. Kind of like what we have to do for, we have to go to college before we can have our full-time jobs. Well, this is actually, it's not being used right now, but this is a blood vessel, and what they do is they run artificial blood through it, and they basically kind of tell it, this is what you're going to do once you get in the body. Okay? Now, this is amazing science fiction type stuff. So I know what you're saying. You're saying that surely there's nothing that we can do that's better than that, right? But there is. And so the next step that's been taken is to actually try to figure out a more efficient way to make these molds, or maybe to even combine the making the mold process and the stem cell process into one. So what's been done is that these are printers. And right now in this top left-hand corner, you can see that's actually a normal printer. That's just something that you could get at Staples or Office Depot. That's actually, they took out the ink cartridge, they replaced that with a cartridge full of cells, and they basically added a 3D leveler. So instead of printing linearly like on a sheet of paper, it's going to print vertically layer by layer. And this is a scientist using that printing machine on the right, and on the bottom, that's just an artist's depiction of what he feels that the printers can look like if somebody like HP gets a big ink. Now the last and the newest idea is to actually take the organs that are discarded, because there's thousands of organs that are discarded every year for various reasons, like somebody might have hepatitis, so they can't donate a liver, or they might have some sort of disease. And so what they do is normally we just throw those organs out. So what scientists are saying is that, well, if we take those organs and we dissolve away the cells from that person, then we're just going to be left with the cartilage, the 2x4s, the structure that makes up the organ, right? And so when you're just left with that, you can just go from the first process, take their stem cells, and then seed away the stem cells, grow them exponentially, and then put those cells onto the foundation, and you're able to build this organ, right? And this is amazing stuff. Now, what is the future? What else are we going to be able to do with this technology? I mean, obviously, this is amazing stuff, groundbreaking ideas. Well, one idea, this is from Wake Forest Institute for Regenerative Medicine. One of their ideas is to actually, is they want to see a bed where basically you'll be able to come into the emergency room and you'll say, have a scab on your hand, and you'll be able to lay down on the bed. They'll have a laser go over and figure out exactly how bad the damage is, and then they'll basically have a machine come over and spray stem cells, kind of like a paint gun, and they'll basically cover up the damaged area with stem cells. And here's a picture. We're able to do the process right now, but it's kind of it's a lot more tedious. It takes weeks or maybe months to be able to make a mold that's going to fit the area. By that time, you're already healed. Another interesting note is that actually, because of all this technology, the UN last year they actually told the world that they need to be prepared for the debate of cloning in their country. That within just a year or two, that there will be serious problems with people having the power to clone an entire human being. And so either your country needs to say, well, we are for cloning human beings, or we are against cloning human beings. Now, I've given you a lot of information about the science of what's going on right now, but I don't want you to lose sight of what the goal of regenerative medicine is. Okay, and so really, regenerative medicine isn't just regenerative medicine. The objective isn't just to make this science fiction stuff true. Its purpose is to be a prevention, and to really instead of treating the symptoms like in medicine we do now, they really want to find the problem and fix the problem before it becomes exacerbated and becomes even worse. Okay, and so I want to tell you real quick about how or show you how this has affected people's lives already.
I was really sick. I could barely get out of bed. I was missing school. It was just pretty much miserable. I couldn't, go out and play, basketball at recess without feeling like I was going to pass out when I got back inside. I felt so sick. I was facing basically a lifetime of dialysis, and I don't even like to think about what my life would be like if I was on that. So after the surgery, life got a lot better for me. I was able to do more things. I was able to wrestle in high school. I became the captain of the team, and that was great. I was able to be, the normal kid with my friends, and because they used my own cells to, build this bladder, it's going to be with me. I got it for life, so I'm all set.
Now that's an individual who had a bladder transplant, like I said, about 10 years ago. And he was one of the first. It was very experimental at the time. He was born with spina bifida, and like you said, he's had problems his entire life. And because of regenerative medicine, it was able to fix this problem that modern medicine wasn't able to even touch. And so really what I want you to understand is that with expansions of regenerative medicine, you can have clinicians understand how this research is engineering really a new future for medicine, and not just for the patients that they're treating, but really for the philosophical problem of treating the symptoms instead of really curing the problems. And so that's what I want you to kind of leave with today, and to really realize that regenerative medicine is about finding a cure. Okay. Thank you for your time.
I'd like to open this up to any questions that you might have of any of our presenters.